All right. Hello, everyone. My name is AIChE. I'm a second-year PhD student at Case Western Reserve University, and thank you for coming to my talk. This cool video that you see playing on the right is showing us fluorescent silica particles that are moving at different velocities throughout the different depths of film, and they're moving downwards as a consequence of gravity. All right. So immediately following the application of coatings onto surfaces, there exists a very complex interplay between the rheology and kinematics, which can give rise to a variety of defects. These defects can happen due to energetic instabilities, which is the case for bubbling and cratering, or it could happen due to air entrapment within the coating, which is the case for blistering and pinhole formation, or it could also happen due to flow-driven instabilities. These flow-driven instabilities could happen due to surface tension flows, which is the case for orange peel deformations, or they could simply happen due to gravitational-driven flows, which is the case for sag defects. And in this work, we're interested in understanding the complex relationship between the rheology and kinematics and the phenomena that leads to sag in automotive coatings. And sag, as you can see from this image, leads to material accumulation down the incline in the formation of a non-uniform surface. So typically automotive coatings are applied onto a car surface via what is called spray application. And many of the defects that you saw on the previous slide occur during what is called flash stage. During this stage, this stage constitutes roughly the 10-minute interval immediately following application. And during this phase, solvent evaporation is taking place and polymer cross-linking is initiated. So any defects that happen are very detrimental. And as engineers, we care about eliminating such defects for many reasons, one of which is the energy-intensive nature of coating process and application, which is estimated to be about 60% of the energy consumption for a single automotive plant. Also, coatings process and application releases about 210,000 tons of ozone-producing solvents into the atmosphere per year, which is about 32% of all VOC emissions. And currently in the industry, anti-sag properties of coatings are analyzed via what is called an anti-sag meter. And it is this schematic right here. It was a very simple visual technique developed by ASTM. It consists of a drawdown bar that has multiple notches of identical width and varying clearances. So upon coating application, you get a series of wet parallel films that have different thicknesses. And then the substrate gets reoriented normal to the ground with the thickest stripe at the bottom. And anti-sag is given by an index value, which corresponds to the smallest thickness in which no two stripes are seen to completely merge together. This technique is very simple and robust in that it could be used for any type of paint. However, it has some drawbacks in that no quantitative information can be learned about the flow fields. And this is mainly because this standard is only done at 90-degree incline and there is no local resolution through the film. So in essence, we can't learn anything about the instabilities that can arise during this process, such as the Marangoni flows. And over the course of the years, engineers and scientists have worked to develop different optical techniques in order to quantify sag. Among these techniques, I'm not going to go into detail, but I will list a couple, such as the indicator band method, the distinctness of image or DOI method, the falling wave technique, or the one I would like to highlight is the one that utilizes particle tracking in order to measure the particle velocity on the coating-free surface in order to get a real-time sag measurement of the coating. So all of these optical techniques are very useful. However, they have the same drawback as the ASTM in that no quantitative information can be learned about the flow field. And this is where our work comes in. So today I'm presenting a new particle-based microscopy technique to non-invasively probe transient kinematics and drying coatings. We hope this technique will help us provide us with real-time quantitative evaluation of sag at any desired orientation relative to ground, and essentially provide us with fundamental understanding of the drying process, so how the paint both physically and chemically evolves. And this technique is called variable angle inspection microscopy, or I'll call it VAIM for short. It works very similar to a regular microscope in which you have light coming in through the light source. This light gets filtered by a filter cube, and then we have a wavelength of about 560 nanometers that gets down to the sample. Our sample itself contains fluorescent silica particles, which get excited by the light, and then they emit back light with a particular wavelength that finally makes it to CCD camera for video capture. What's unique about our setup is that it includes a piezo-controlled objective. So the scan process in and out of the volume of film is an automated process. And also it includes this 3D printed mount that was designed with SolidWorks that helps secure the sample in place as it gets rotated to any desired orientation. And we call it variable angle inspection microscopy because it could be rotated to any angle. As you can see from these images between 0, 10-degree incline, 45, and 90, it's not only limited to those four, and it could basically rotate 360. And that's thanks to this goniometer piece back here that allows us to rotate it. So in order to utilize a particle tracking technique, the first thing we had to do was synthesize the fluorescent silica particles. And this was done in accordance to Stober method. As you can see from my SEM images, we synthesized particles that are about 1 micrometer diameter. The next step is then sonicating these particles in solution in order to ensure homogeneous distribution in the sample. And we used particle fraction of about 0.09%. Next is the film application, which utilizes, as you can see from the video, an automatic drawdown machine. And all of the samples that you'll be seeing in the results were applied at the same speed of 25 millimeter per second. Lastly, we do video capture and video analysis in which we do particle tracking, and we measure the particle velocity throughout the different depths of film in order to learn about the flow field. So prior to conducting experiments, the first thing we have to do is design a very efficient piezo scan code that can go in and out of the volume of film. For that, we use a surface analyzer in which we conduct continuous scans for the film and track the region of interest in which all of our experiments were done at, which is about 1/3 of the distance upstream. And from that, we can learn how the film thickness is decreasing over time, which is represented by these red dots. The next thing is then we use a calibration slide in order to locate the solid liquid interface. And now that we know how the mobile boundary is decreasing over time, and we're able to locate the solid liquid interface, then we can design a very efficient piezo scan code that can start scanning from the coating-free surface, move deep down into the microscope slide, and then back up to the free surface in an oscillation fashion. For the experimental conditions in this work, we used 3 different petroleum-based mineral oils. We chose those because they have a viscosity that resembles that of coatings. The orientations were 5 and 10-degree inclines, and the film thickness for all results were about 150 micrometers, and the sample volume used is 80 microliters. So with all of these variations, we were able to evaluate sag velocity as a function of height, time, and viscosity. And this is what a typical results plot looks like. So the solid black line represents the film thinning process, which is measured with profiliometry. And these dots represent the particle velocity throughout the different depth of film. The brightest dots that you can see here represent the particle velocities at the free surface, which are measured to be the highest. The velocity decreases as we move deep into the film, where it reaches a minimal value at the solid liquid interface, represented by the black dots. So one thing you can see from looking at this plot is that as the film thickness is thinning, the velocity measured throughout the film is also decreasing. So upon inventing this new technique, the first thing we did was test repeatability. And this plot is really exciting to me because it shows us that, as a matter of fact, we can repeat all of our VAIM measurements. And this was true for the various viscosity standards at both orientations which were evaluated. Some of the observations that we saw was that increasing the angle of incline resulted in larger velocity measurements. So looking at the red dots, which represent the particle velocities at a 10-degree incline versus the same viscosity standard at a 5-degree incline, increasing the angle of incline caused an increase in gravitational forces acting on the film. Thus, we were able to get higher velocity measurements. The other observation is that increasing viscosity results in smaller velocity measurements. So looking at the maroon and the red dots, which represents the least viscous samples, compared to the black dots, which represents the most viscous, we can see increasing viscosity increases the force which opposes flow, and as a consequence, we were measuring smaller velocity measurements. So the next thing we did was then model our data, and for that, we conducted a good old momentum balance, assuming Newton's law of viscosity, and choosing appropriate boundary conditions, such as at x is equal to 0, we have 0 shear, and at x is equal to HT, which is the film thickness. At the solid liquid interface, we have maximum shear or 0 velocity due to no slip assumption. With that, we arrived at the sag velocity equation that you can see here, which takes into consideration material properties such as viscosity and density, and it has two time-dependent variables, which are HT, the exact film thickness at that time interval t, and XT, which is the exact piezo position in which we were taking videos. So what's unique about this equation is the way we're employing it, because we know the exact film thickness and the exact piezo position. So essentially, we're getting local velocity measurements of the particles throughout the film. Next, we modeled the thinning process during what we call gamma fit. So this modeling was done assuming constant volume deformation over time. And sag, which is represented by DLTT, which is the change in volume in sample length over time, is a combination of both average velocity, which is obtained from the Navier-Stokes model, in addition to a gamma fitting parameter. This gave us this mathematical expression. If we integrate using the appropriate boundary conditions, then we were able to get the exact film thickness at that time interval t. And this model fits very, very nicely with the profilometer measurements, as you can see here. So this is another exciting plot for the measured versus theoretical values that we got from the model. So this is really nice because it shows us that these values are in both quantitative and qualitative agreement. So going back to our main motivation, which is to use this technique to probe complex fluids, what I'm showing you here is two graphs. The one on the left is showing us 3 experimental repeats for an acrylic-based clear coat that has a viscosity of about 0.15. This viscosity was measured in microrheology. If you're interested, please see my colleague's talk on Wednesday. And what I would like to know about these two plots is that you can see the dots don't quite as nicely overlay on top of each other as that was the case for viscosity standards. And that's because of the complexity added to the coatings. And even for modeling the sag velocity throughout the film, we can see there's a little bit of a discrepancy due to those added complexities. So with that, I would like to give some take-home messages and acknowledgements. VAIM allows us for tracking velocity of particles in a film about 150 micrometer with known viscosity. And these probe particles were tracked at speed as high as about 100 micrometer per second. The sag flow fields were well resolved in a 100 micrometer slab. So finally, VAIM is very effective at relating material properties to flow kinematics. And with that, I would like to thank my PI, Dr. Christopher Worth, my colleague, student Haru Yu, and all of our collaborators at Lehigh University and PPG. Thank you.